All right, folks, so we have some bouncing working, kind of, but it's really not good. You have some weird errors where I love the ball slide. Like the ball is coming in and then it slides through and then it gets ejected, right? So the problem is that this code here isn't really what we want. What happens is, like, especially if you notice it happens when the ball hits at the bottom, right? So the ball hits at the bottom, and then we change the Vx so it's going this way now, so its trajectory starts going that way, but then it just ends up in the paddle still. So then it bounces again, and then now it's really inside. So it just keeps bouncing over and over again, and then finally it gets to the top, and then it gets ejected out the side. So that's not great. Sometimes it works okay. Like if it hits here, it's not so bad. But then sometimes your paddle's moving so fast it like catches it and it gets stuck inside too. So these are clearly, like, here is just wrong. So it's good for walls because walls don't move and they're not round. So it's not good for paddles. So let's get rid of that line of code. We're going to remove it and we're going to do something a little bit more clever. So here's the story behind circular collisions. And this is one of the reasons why I want to use a circle. I know some of you Pong purists are like, but no, they're rectangles. And I totally appreciate that. And if you want to, at the end of the project, you're going to have a chance to add in your own features. So if you want to make like a switch that turns into rectangles and does different math, that's actually pretty fun, especially if you like math. But do make sure for the basic project you're using circles. And here's one of the reasons why it works. Ooh, that's a good circle, hey? Whew. I'm teaching math for the first time in a few years this year, so I've got to practice my circles. So anyways, here we go. Let's say that's our paddle. Here's like the wall. And then here's the ball coming in. So let's just do a quick thought experiment about what the ball's going to look like when it bounces off. Let's imagine the ball's coming in this way, and it hits like right on the edge here. Like right now, you can imagine what direction it's going to fly off, right? It's going to hit that. It's going to like bounce off, like kind of like off in that direction. Yeah? Looks like checks with what your imagination would be. Say it's coming in this way, and it hits like right on here. That's probably going to kind of bounce off like that way, right? So how do we turn that into math? Because computers, they can't look at it and just use intuition. And I mean, at some level, we're doing some kind of math too inside of our head, but we don't really experience that. It just feels like, oh, I just know the answer. Computers have no intuition. They have to break it down into exact numbers. So it turns out the way we can do this is very similar to some of the math problems you solved in grade 9 math. Do you remember all those x, y graphs? You had to draw straight lines and y equals mx plus b and yeah, all that stuff. It turns out that math is like critical to video games. I don't know why all the examples don't involve video games. It seems like the obvious thing to like get students like interested in how this is working. But if I gave you a question, just to put that aside for a second, if I gave you a question where I was like, here's 2 points on a line, what is the equation of the line in the y equals mx plus b form? You could probably figure that out. You could probably figure out what the rise and run is to get the slope, and then you can figure out what the y-intercept is and plug that in, right? It's going to be actually very similar process we're going to do here. So what we need to find the slope of is the line that the ball is going to shoot out from. And that line is really easy to find. It's just going to be if you connect the centers of the two circles, that's the line it comes off on. Do you see how, like, if it hits right on the edge, like that there is the line that's going to bounce out at? So if we find the rise and run, the Vx and Vy of that line, then we'll be good to go. Same with this direction here, right? It's bouncing off in that direction. Like, I kind of missed my center there, but like we just connect the two circles and find out what the rise and run of that is. There'll be one last thing we have to do after that, but basically that's the whole math. We need to figure out what is the rise and run here. So I'll just redraw this to get a little bit more clear of a diagram. Hopefully you feel like the plan makes sense, at least in terms of the visual, right? It looks like that's the direction it should bounce off in. Inferior circle. We'll have to go with it. So let's just draw this one a little bit bigger. So I'm assuming this is the paddle and the ball. You'll have to do this for both paddles, by the way, just like the other if statement. This if statement, you have to do one for each paddle. So these calculations will be, the two different sets of calculations. So first of all, I want to find the slope of, maybe I'll use red. I want to find the slope of this line. If I can find the slope of that line, then I can use the Vx and Vy that give me that slope, the rise and run that give me that slope, to send it off in that direction. So to find that, I basically need sort of this information here, and I need, dare I use another color? I had a blue, here it is. This is the rise, and that's the run. If I can figure out that information and make that my new Vx and Vy, then it will move along that slope. So this is going to be our Vy, and this I should have used green or something. I don't know. I'll just use Vx for red. These numbers, if we calculate them based on these sizes, it's going to be too big. So stay tuned. We're going to figure out what they are first, but then we got to shrink them down because that's just too large of a rise and run. We'll get the right slope, but we'll just be moving too fast. So anyways, how do we get that number? So the way we get that number is just to take, for Vx, we just take the difference of the two x coordinates. So we have whatever the ball's x here is called, and we have whatever the paddle's x is called. If we take the difference of these two numbers, we'll get that size, right? If we draw the larger screen here, like if this is sort of our window, this x coordinate, I guess that's not going to be the window. It might be 0 for us. But just to illustrate, this is the distance for the x coordinate here, and that's the distance for that x coordinate. So if we do this minus this, we get that. So we just basically take the difference of the two x coordinates to find out what our run will be. And it's the same thing for finding this y coordinate, or this rise. It's going to be the difference of sort of the paddle's y and the ball's y. So that's the paddle's y, that's the ball's y. If we subtract, one minus the other, we'll get the remaining quantity. So that's how we're going to find out what these different numbers are, and then we can just replace our Vx and Vi with those new calculations. So instead of timesing Vx by -1, we're going to do something like this. We'll say Vx is going to be the difference of the two x's. And I think it's almost always going to be ball minus ball minus paddle. So whatever the ball's coordinate is minus the paddle. And if we mess it up, what you'll see is instead of going out, it'll go in. So if you see your ball getting sucked into the paddle center, then you know that you just got it backwards. But I'm pretty sure it'll be whatever your ball's x coordinate is. What is everyone's ball's x coordinate called? Ball x? Yeah? So it's just like ball x, and then minus the paddle's x. So this might be left, it might be right. I'll just put px because you're going to have two different if statements, so this will be left or right depending on what it is. And same with Vy, it's just going to be ball y minus paddle's y. So we're not quite done though. If you do this, it's not bad. You'll go in the right direction, but it will blast off so fast because it's going to move this much and this much every frame. And that's just too much. We're going to go off in an incredible speed. What I'd rather have is, I'd like to keep the slope, but I'd like to have a smaller Vx and Vy, right? Like reduce this so that I just move a little bit along the same slope, but just not so fast. So how can I get this smaller triangle with a smaller Vx and Vy, but still keep the same slope? Well, if you divide both the rise and run by the same number, then you'll keep the slope, but the rise and run will be smaller. So we can just divide this by some number. You can play around with what number that is. It's your choice. You can decide. And it's going to depend on your ball size and your paddle size. So if you have a big paddle and a big ball, you might have to divide by more. If you have a small ball and a small paddle, like maybe you'll divide by less. It kind of depends on how big these distances are anyways. But I would do something like just divide by 10 to start with. So I'll put this in parentheses because if I didn't, then bed mass would make the division happen first. Although, processing isn't smart, it does know bed mass. So we should put that in parentheses and then divide by, say, 10. And then again, that number might not work for everybody. Yeah, it might not work for me either. So we might have to try 5 or 15 or 7 or 3.4. Like you just play around with it until you get a good speed. And so if you put this in, you're going to have the two if statements, right? One for the left paddle, one for the right paddle. Basically the same calculation in both. It's just which variable you use. One will use the left paddle's variables, one will use the right paddle's variables, and that should get you bouncing off of the paddle. So give that a try, and if you get it working, it's going to feel so good. It's just going to look like it bounces correctly. There'll still be a couple of problems. Just to let you know, before you go any further, here's a couple of problems that will happen, and we'll solve these. But if this is your screen, and the ball is like down at the bottom, and your paddle is like right here, and you're moving down, you could like crush the ball into the bottom here, and you end up getting it like bouncing sort of down here, or maybe it'll look like it's gone completely away, like it's like been knocked underneath the screen. Same thing can happen at the top of the screen as well. The original designers of Pong solved this problem by just stopping the paddle here. You just couldn't go higher or lower. It actually made the game a little bit more fun because you can never be perfect. Like, you could aim for that tiny corner there and you could, solve that problem. So that might be one way to solve it, just preventing your paddle from going too high or too low. But we'll have to take a look at that solution. There's a couple of little things that might still happen even after you get this math correct and everything's working. But don't worry, we'll have future videos about perfecting those things. So as long as it's mostly working for most cases, you're doing it right. So thanks everybody. I'll let you try that out now, and I'll leave this up on the board, and folks in the YouTube video, hi, I hope that made sense. Ask on Teams.